Every single day, at the Lockheed Martin factory in Fort Worth, Texas, fighter jets roll off the production line, ready to dominate the skies. This is where the legendary F-16 Fighting Falcon is assembled, each one a true engineering marvel. In just 52 days, hundreds of specialists, robotic systems, and thousands of components come together to create a combat machine capable of reaching speeds of 1,500 miles per hour. How is this steel predator built? I visited the factory and saw it all with my own eyes. Ready to dive into the heart of aircraft manufacturing? Buckle up, we are taking off. At the massive Lockheed Martin factory in Fort Worth, Texas, the day begins with the roar of machinery. Gets the adrenaline pumping, right? My heart is racing. Here, in the heart of aerospace engineering, one of the most famous fighter jets in the world, the F-16 Fighting Falcon, is brought to life. But the process of building each F-16 begins long before the first part arrives at the factory. Engineers at Lockheed Martin start by working with 3D modeling systems using CATIA V5 and Siemens NX software. A digital twin of the aircraft is created to test virtual aerodynamics, simulate material strength, and optimize the placement of cables, pipelines, and electronic systems. After that, supercomputers run numerous simulations to predict how the F-16 will perform at different speeds, in combat maneuvers, or under extreme temperatures. To test the strength of the structure, prototypes of key components, such as the wings, nose section, and tail, are built and subjected to rigorous lab tests. They undergo vibration-resistant simulations to mimic turbulence, as well as extreme temperature exposure, heating up to 302 degrees and cooling down to minus 76 degrees Fahrenheit. And let's not forget impact resistance tests, like simulating a bird strike at 559 miles per hour. You love crash tests too, right? It is thrilling. Meanwhile, a separate team works on the cockpit. Test pilots evaluate the ergonomics of the instruments, the positioning of the HUD display, and the ease of control. As for the materials, supply issues are never a concern. Lockheed Martin signs contracts 2 to 3 years in advance. The standard material set includes aluminum and titanium alloys from Alcoa and Timet, which form the fuselage structure, composite materials from Toray and Hexil, used for wings, fairings, and radar-absorbing elements. Aerospace electronic systems, including radars, avionics, and targeting systems, are provided by Northrop Grumman and Raytheon. In the morning, the factory floor at Lockheed Martin has a quiet but focused atmosphere. This is not just manufacturing. This is where fighter jets that will rule the skies are born. Workers are at their stations. Some are prepping riveting guns. Others are reviewing blueprints, while some are operating laser measuring systems. Today, another F-16 Fighting Falcon is being assembled, and everything must be flawless. As you might have guessed, the factory follows a modular approach. Instead of building an entire jet in one place, it is assembled in sections before being joined together. In one of the workshops, the aluminum cockpit frame is already complete. Nearby tables hold avionics instruments, HUD displays, and computer system modules. Workers in white gloves carefully install them into compartments. The ejection seat mount is fitted, and a 12mm thick bulletproof canopy glass is installed, capable of withstanding a 13mm bullet impact. 12.5 miles of wiring are laid out, connecting sensors, displays, and control systems. Meanwhile, the central fuselage section is being assembled, the area that houses the fuel tanks, landing gear, and wing mounting points. A large aluminum frame is secured with 40,000 rivets installed by automated riveting robots. Fuel tanks with a total capacity of 845 gallons are integrated into the structure. The landing gear, capable of handling loads up to 44,000 pounds, is installed and tested. Workers meticulously check the tanks for leaks by filling them with a special gas and inspecting for any seepage. In the adjacent workshop, the tail section takes shape. It is welded together using titanium and composite panels, with an engine mount already in place, designed to withstand temperatures exceeding 2,192 degrees Fahrenheit. The elevator and rudder are then installed, followed by a check on the emergency braking mechanism. A specialized team handles this section since the tail not only controls flight, but also maintains the jet's overall balance. The wings are assembled in a dedicated section. Hydraulic mechanisms for controlling flaps and ailerons are installed, along with hardpoints for weapons. The composite wing surfaces undergo ultrasonic testing for defects. If even one layer of carbon fiber is improperly placed, the wing could deform under combat stress. So there is zero tolerance for errors. Once all modules pass rigorous inspections, they are transported to the final assembly line. The final assembly line is a massive hangar stretching 437 yards long, where hundreds of specialists work in precise coordination. Everything follows a strict schedule. Any delay in one step can impact the entire process. The central fuselage is lifted by a specialized crane and aligned using lasers. First, the cockpit is attached, followed by the tail section. Engineers use high-strength titanium bolts capable of withstanding loads of approximately 88,180 pounds. Once the primary structure is complete, it is time to attach the wings, which are secured with reinforced titanium joints to ensure structural rigidity. Engineers meticulously check the alignment angles to ensure the error margin does not exceed allowable limits. After assembling the airframe, one of the most critical moments arrives: the installation of the jet engine. It is transported in a specialized container and lifted into the tail section using a hydraulic hoist. Technicians carefully connect all systems: fuel lines, hydraulic and electrical cables, and the afterburner system that enables supersonic flight. Once installed, a dry test run is conducted to verify its operation without fuel ignition. The onboard computer, pilot displays, weapons control systems, and the ANAPG-83 radar, capable of detecting targets at a range of 100 miles, are then integrated. Before the first flight, the F-16 receives anti-corrosion treatment, paint, and stealth coating. As a kid, my best friend was obsessed with origami. She was into everything from Eastern culture, so origami never stood a chance of being ignored. Me? I was terrible at it. My fine motor skills were not exactly top-notch, so while she was crafting intricate dragons and delicate flowers, I was busy making paper planes of all sizes and launching them from my window into the backyard. Could I have imagined back then that I would one day step into the legendary Lockheed Martin factory and witness the birth of an F-16 with my own eyes? Absolutely not. Before an F-16 takes to the skies, it must undergo a series of ground tests. Every flight system, electronics, fuel supply, and hydraulics is tested on the ground first. The engine is warmed up to operational temperature, and the exhaust system and airflow temperature in the ducts are inspected. Special attention is given to the ACES-2 ejection seat and emergency systems that might be needed in a crisis. Once all ground systems pass, the pilot receives clearance for the first flight. Communication with ground controllers and engineers is checked in real time. The jet slowly rolls toward the runway, then accelerates to around 3,000 yards per hour for an optimal takeoff. After liftoff, the landing gear retracts smoothly. Everything is functioning perfectly. At an altitude of around 3,300 yards, the pilot executes the first maneuvers, testing aerodynamics, elevator, aileron, and flap responses at different speeds. The F-16 is then pushed past Mach 1 to test the afterburner system. This phase measures aerodynamic stress, identifying any defects at high speeds. G-force tests follow, as the pilot executes precise maneuvers to ensure stability under varying attack angles and velocities. After completing initial flight tests, the pilot begins the descent. At 3,000 yards, the landing gear deploys, and the pilot prepares for touchdown. The effectiveness of brakes and the auto-stabilization system is evaluated. The moment the F-16 touches the ground, it decelerates quickly. Engineers conduct final inspections of electronics, fuel systems, and structural integrity. Data is then analyzed, and if everything checks out, the F-16 is officially cleared for duty. Do you know what can amaze you even more than the flight of an airplane itself? It's life after the sky. Every year, thousands of airplanes are retired worldwide, and some of them become a source of metal for new automobiles or even construction frameworks. One single Boeing 747 contains around 165,000 pounds of aluminum, which can become the future raw material for dozens of other airplanes. Are you curious to learn how engines, which can cost up to $30 million, get a second lease on life? Or how first-class seats turn into part of a home movie theater setup? Are you ready to journey into a realm where technology, ecology, and business converge in one enormous hangar? Let us take off and explore. The first step in a retired airplane's journey is what insiders often call its removal from flight. In fact, this phase is sometimes referred to rather poetically as heading into retirement. Airplanes are retired when they reach a certain age, a certain number of flights, a certain tally of hours in the air, or when they simply become economically unviable to operate. Passenger airplanes typically serve from about 20 years to about 30 years. The metal gradually becomes fatigued from the repeated cycles of takeoff and landing, alongside the persistent air pressure at cruising altitudes. Engineers may detect microcracks or other structural issues, making further flights risky. Older airplanes require more frequent maintenance, which becomes expensive. Eventually, the costs of upkeep can overshadow any profit from keeping that aircraft in service. More modern airplanes consume less fuel, are cleaner for the environment, and cost less to operate. For instance, contemporary designs, such as the Boeing 787 or the Airbus A350, are far more efficient than older airplanes like the Boeing 747. International safety standards also keep shifting. If an airplane does not meet new standards and modifications prove too pricey, that airplane is retired. Occasionally, airlines retire airplanes because travel demand declines. During the coronavirus disease 19 pandemic, many older airplanes were retired ahead of their original timelines. Interestingly enough, cargo airplanes can keep flying for a longer period as there are fewer requirements for passenger comfort and their overall load can be lighter. Yet sooner or later, even cargo airplanes head into retirement. Once an airplane is ready for disassembly, it is towed to a specialized hangar, where its second chapter really begins. The first priority is the engine. They are, beyond any doubt, the most valuable part. Engineers remove them first, perform detailed inspections, and then either overhaul them for reuse or break them down for spare parts. One of the staff members told me that a single engine can be more expensive than the entire airplane. Can you imagine that? The process starts with engineers reviewing the documentation for both the airplane and the engine. They want to know its overall condition, its servicing history, and whether any special precautions are needed. All fuel, hydraulic fluid, and lubrication systems in the engine are de-energized, with every liquid drained. This step is crucial, since even small amounts of leftover fuel or oil can be a fire hazard. The engine is linked to the airplane by dozens of cables, pipes, and mechanical connections. One at a time, engineers disconnect the electronics, hydraulic lines, and ventilation and cooling systems. All connectors are labeled so that they can be quickly identified whenever the engine is inspected or installed on a different airplane. The cowling is the protective shell around the engine. It is taken off to reach the main components underneath. This cowling is removed very carefully and often sent away on its own for inspection or repair. Engines can weigh several thousand pounds, so they must be firmly supported before removal. Specialized lifting platforms or cranes are used to ensure the engine remains undamaged during detachment. Engines are attached to the wing or fuselage by pylons, which are special mounting structures. Engineers gradually remove these attachments, frequently by hand, using high-precision tools. It is a delicate moment, since a slip can cause damage. Following removal, the engine travels to a service facility for inspection, repairs, or further disassembly. It is secured in a dedicated container that safeguards every part during transport. The engine is the priciest piece of the airplane. Depending on the particular model, it may cost anywhere between $10 million and $30 million. As a result, the removal process is carried out with extreme caution. Often, an engine is not taken off because of a failure, but rather to undergo planned maintenance, or so it can be installed on another airplane. In many cases, engines embark on a new life after refurbishment and upgrades. This underscores yet again that aviation is not just about flying, but also about pragmatic reuse and a certain technological artistry. The next thing that amazed me was the fuselage. The aluminum body of an airplane is not simply chopped into random pieces. Instead, it is sorted, cleaned, and directed toward recycling. This metal can be reborn as part of new airplanes, car parts, or even building materials. By the way, have you ever wondered how much aluminum is inside a single Boeing 747? It is about 165,000 pounds, which is impressive to envision. That quantity could practically spawn an entire fleet of future airplanes. Seats, which we usually see as nothing more than comfortable chairs for our flight, can also be reincarnated. They are repaired and sold to airlines that have tighter budgets. Sometimes they even end up with private buyers. Did you know that first-class seats can be purchased for a home movie theater? That idea is definitely on my personal wish list. Aviation electronics form another treasure trove. Every component, from onboard computers to navigation systems, is extracted and carefully evaluated. These parts often see further use in pilot training simulators or get integrated into other airplanes. Even seemingly small items, such as life vests, seatbelts, or tableware, find new owners. Some of them are turned into unique souvenirs. Do you recall those movies in which people collect aviation memorabilia? That is actually based on reality. Aviation collecting can be quite costly. For instance, the nose section of an airplane or an antique propeller can sell for thousands of dollars. If a piece is historically significant, say it comes from an airplane involved in the Second World War, its value could multiply dramatically. The aspect that left me most astonished was the team's flawless coordination. They moved as if they were dismantling a gigantic construction set, with each part assigned its own special place in the bigger picture. It was almost like a dance involving both machinery and people, all working in harmony to accomplish something meaningful. Think about it. A single airplane can yield up to 50,000 parts. Someone has to track each nut, each bolt, and each panel, making sure everything lands in the right container. Logistics teams then see to it that no part gets lost and that every component reaches its intended destination, whether it is a repair center or a recycling facility. Disassembling an airplane is definitely not a matter of taking it apart and forgetting about it. Proper disposal protocols must be followed for all hazardous substances, such as unused fuel, hydraulic fluids, and batteries. Environmental teams and safety inspectors ensure that every step complies with regulations and safeguards the planet. Having witnessed all this, I am convinced that aviation is so much more than just flying. It is about ecology, business, and even a touch of art. Now, whenever I look up and see an airplane cutting across the sky, I find myself wondering what the future holds for it. How about you? So the next time you watch an airplane soar overhead, remember that even after its final flight, it can transform into something far greater. What do rockets and a fabric stronger than steel yet lighter than plastic have in common? And how do engineers create technology that withstands 17 million pounds of thrust, the freezing cold of space, and temperatures in the thousands of degrees? Today, we'll uncover the secrets behind rocket construction, from revolutionary materials to million-dollar final tests. Get ready, this journey will leave you in awe. First off, a rocket isn't just a metal cylinder with engines, as it might seem at first glance. Turns out, many of its components are made of advanced materials called supermaterials. Take carbon fibers, for instance. They're incredible. Imagine a fabric that's lighter than plastic, but stronger than steel. These fibers are woven into thin layers, almost like a carpet, then infused with special resins and baked. This process creates the rocket's body, capable of withstanding extreme stress. Picture this. In just 1 square inch of carbon fiber, there can be up to 50,000 individual fibers. Each one is only a few micrometers thick. That's thinner than a human hair. Let's dive deeper. Carbon fibers are made from a polymer called polyacrylonitrile, or from carbon residue in petroleum. The process begins with long, thin threads of this polymer. These threads are heated to extraordinarily high temperatures, up to 5,500 degrees Fahrenheit. During this process, organic components are removed, leaving nearly pure carbon composed of tiny yet incredibly strong crystals. These crystals in carbon fibers are aligned in one direction, like perfectly arranged bricks in a wall. This alignment gives the fibers extraordinary tensile strength. Plus, they're highly heat resistant, making them perfect for the harsh conditions of space, where temperatures can swing by hundreds of thousands of degrees in either direction. For rockets like the Falcon 9 from SpaceX, carbon fibers are often combined with epoxy resin to create composite materials. These composites are used for fuel tanks, bodies, and even protective shells, anything that needs to be strong yet lightweight. Carbon fibers are produced in specialized factories, most of which are located in Japan, the United States, and Europe. Companies like Toray Industries and Hexcel are leaders in this field. From these factories, the fibers are shipped to facilities where rockets are built. The weaving of carbon fibers happens on specialized machines called automatic winding machines or robotic braiding systems. At the center of the process is a massive mold shaped like a cylinder or cone, which becomes the rocket's body. Fibers are carefully wound around this mold. The winding isn't random, it's precisely calculated. Layers of fibers are laid at different angles to ensure maximum strength and resistance to stress. It's similar to making plywood, multiple layers with different grain orientations, but on a nanotechnology level. This research took me a long time, and I pieced together this video frame by frame over several weeks to show you. I hope you enjoy it. Now, let's see what happens next. After the body is woven, it's time for the resin. Resin is evenly applied to the fibers to create a strong composite. Think of it as gluing layers of paper together, except instead of paper, you have carbon fibers, and instead of glue, you have specialized polymer resins. Once the body is ready, it goes into a massive oven called an autoclave. Here, at about 400 degrees Fahrenheit, and under high pressure, the resin hardens into an ultra-strong material. This step is critical because, without it, the body couldn't withstand the enormous stresses and temperatures during a rocket launch. This process typically happens in specialized hangars or production facilities. For example, SpaceX's Gigafactory, enormous, immaculately clean spaces. Robots and automated systems control everything to ensure not a single speck of dust interferes with creating the perfect rocket body. The size of the machines and molds is staggering. Imagine a cylinder tens of feet long and several feet in diameter. Access to these top-secret facilities is required to witness this incredible machinery in action. They say it's a sight that's out of this world. As you might guess, I couldn't see everything with my own eyes. The completed SpaceX Falcon Heavy rocket is 230 feet of pure engineering brilliance. It weighs over 3 million pounds, that's the weight of about 7 blue whales, and can lift 140,000 pounds of cargo into orbit, more than a fully loaded Boeing 737 with passengers, fuel, and luggage. Titanium and aluminum alloys are the foundation for many rocket components that require a combination of lightness, strength, and resistance to extreme temperatures. Fuel tanks must withstand immense pressure and temperature changes since they store cryogenic liquids. Aluminum lithium alloys, which are lightweight yet incredibly strong, are often used for this purpose. Turbopumps frequently use titanium. It's not only strong, but also highly corrosion resistant, which is crucial since these components constantly interact with aggressive substances like rocket fuel. The rocket's frame, as well as various mounts and connectors, are often made from aluminum alloys to reduce the rocket's overall weight. But when additional strength is needed, or components face extreme loads, titanium is the go-to material. Some engine parts, such as combustion chambers or structural components, can also be made from titanium alloys. They handle high temperatures and vibrations during engine operation with ease. For reusable rockets like the Falcon 9, titanium is used for legs and parts that ensure reliable landings. For example, the famous titanium grid fins of the Falcon 9 allow the rocket to adjust its trajectory during re-entry. In short, these metals are like the skeleton and muscles of the rocket. One provides lightness, the other unparalleled strength. Next, we were taken to a workshop where every inch seemed to breathe technology. Honestly, I initially thought I had stepped onto a sci-fi movie set. robotic arms, lasers, and 3D printers, creating components from metal powder, all working together like a symphony. These 3D printers are a game changer. Instead of cutting components from blocks of metal, they build them layer by layer. What's fascinating is that this not only saves time, but also allows for shapes that were previously impossible to create. For example, internal parts of fuel pumps are now printed as complex grids, making them lighter and more efficient. And now, the most exciting part, final assembly. Rockets are assembled step by step, the lower stage, middle, and upper stage. Every segment is inspected and tested for proper fitting. Engines are a story of their own. They're installed last, like crown jewels. And these engines, they're engineering marvels. They generate incredible thrust while operating with the precision of a Swiss watch. Each rocket comprises over 100,000 individual components. Every single one must work flawlessly, because even the smallest mistake can turn a billion-dollar project into a pile of scrap metal. Some rocket components are assembled in rooms cleaner than hospital operating theaters. For instance, satellites or optical instruments are built in clean rooms where air is filtered to remove even the tiniest particles of dust. The staff wears protective suits because even a single speck of dust could damage the electronics or optics meant to function in outer space. Once assembly is complete, the rocket undergoes a series of tests. Picture a massive platform where the rocket is secured and ignited at minimal power. Engineers check everything, from tank pressure to engine behavior. One of the most fascinating steps is simulation. Special chambers recreate space conditions: vacuum, low temperatures, and radiation. The rocket must prove it's ready for any challenge. Each rocket launch can cost up to $100 million, roughly the price of 50 Ferraris for just one moment in space. Impressive, isn't it? The sound wave from a rocket launch is so powerful, it can destroy not just buildings, but the rocket itself. That's why facilities like NASA or SpaceX conduct acoustic tests. Rockets or individual components are placed in special chambers where massive speakers and water cooling systems create a sound that mimics a launch. This ensures the rocket's parts won't break under the immense sound pressure. Acoustic tests are mind-blowing. Imagine a sound exceeding 160 decibels. For context, human pain starts at 120 decibels. These powerful speakers literally bombard the rocket with sound to check if its components can withstand the pressure. Finally, after months or even years of work, launch day arrives. Standing in front of a massive monitor, I felt the world come to a halt. The countdown, the roar of the engines, the clouds of smoke, and the rocket rises into the sky, leaving a fiery trail behind. This is the moment when every bolt, every detail, and the efforts of hundreds of people come together. When a rocket launches, its engines generate over 17 million pounds of thrust, enough to lift an entire island or power a small town for an hour. Before a rocket launch, tons of water are poured under the launch pad. And no, it's not to put out fires, it's to reduce sound pressure. Without this, the acoustic wave from the launch would be so strong it could damage the rocket within seconds of liftoff. When I first set foot in this facility, I had no idea how much work and innovation goes into every launch. But now, sharing all this with you, I'm even more in awe of what human imagination can achieve. Rockets are a true symbol of how far we can go when we set ambitious goals. How do you build an engine that can handle temperatures over 3,200 degrees Fahrenheit and carry a Boeing jet across the ocean? Sounds like science fiction, right? But this is the reality of modern engineering. Imagine this. Every single part, from turbine blades to combustion chambers, is crafted with micrometer precision. Metals that don't melt under extreme heat and 3D printing that's changing the game. Dive into the process of creating the heart of an airplane, where every inch truly matters. This is the magic of technology. Turbofan engines that power sky giants like Boeing and Airbus planes might seem like something straight out of a sci-fi movie, but they're the pinnacle of engineering genius. So how do you take tens of thousands of parts and ingredients, almost like puzzle pieces, and turn them into these incredible machines? Ordinary metals simply won't cut it. These engines have to function in conditions where temperatures soar above 1,800 degrees Fahrenheit. That's hellishly hot, and regular steel just can't take it. Enter titanium alloys, lightweight, incredibly strong, and heat-resistant. For the hottest parts of the engine, nickel-based superalloys are used. And trust me, these are no ordinary metals. They're 21st century alchemy. Carbon fiber composites, by the way, are used in the fan blades to reduce weight while maintaining strength. This extreme heat is generated during the combustion process in the engine's combustion chamber, arguably one of the most critical components of a turbofan engine. Here's how it works. Aviation fuel, typically jet fuel, mixes with air and ignites, producing superheated gases. These gases accelerate to insane speeds and temperatures, often exceeding 1,800 degrees Fahrenheit, sometimes even reaching 2,700 degrees in modern engines. This heat is vital for achieving maximum thrust efficiency. The hotter and faster the gases, the more energy they produce to drive the turbine and propel the aircraft forward. Here lies the ultimate challenge. The engine not only needs to endure these extreme conditions, but also perform flawlessly without a single hiccup. That's why cutting-edge materials like titanium alloys and specialized composites are a must. They can withstand both extreme heat and intense mechanical stress. You know what's truly mind-blowing about making these engines? Even individual components like turbine blades are crafted with micrometer precision. For example, blades are cast in a vacuum to ensure they're free of even the tiniest cracks. Some blades are designed with a single crystal structure, meaning the metal has zero seams. But wait, there's more. 3D printing? Yup, it's used too, especially for intricate parts that traditional casting just can't handle. Turbine blades are the heart of the engine. They operate in the hottest zone, converting the energy from the hot gases into rotational movement. First, a wax model of the blade is created. It's almost like artistic sculpting. Only here, precision down to micrometers is crucial. This wax model is then dipped into a special ceramic solution, which hardens into a strong mold. The wax inside is melted away, leaving a perfect cast for the blade. The ceramic mold is now ready for the most critical stage. Now comes the real show. Superalloys, made of nickel, chromium, and other heat-resistant metals, are melted in a special furnace to temperatures exceeding 2,000 degrees Fahrenheit. This molten metal is poured into the ceramic mold. But here's the catch. It's not just about the material, it's about how it's done. To ensure the blade can handle enormous temperatures and stresses, it's often cast as a single crystal. This means the entire piece of metal has no seams, micro cracks, or grains like regular metals do. Why is this important? In these conditions, seams or cracks are like a ticking time bomb. One small flaw, and the blade fails. Single crystals are grown through a slow cooling process. The mold filled with molten metal is gradually lowered into the cooling zone of the furnace. This process can take days, but the result? A blade that's incredibly strong and durable. Once the metal cools, the ceramic mold is broken away, and the blade undergoes meticulous polishing. A special heat-resistant coating may be applied to help it withstand extreme temperatures even longer. And yes, each blade is inspected individually. Even the slightest defect means it won't make the cut. Fuel nozzles, combustion chamber parts, or even compressor blades in aviation are often made using 3D printing. For instance, GE Aviation prints fuel nozzles for its engines that are 25% lighter but 5 times stronger than traditional ones. Layer by layer, using powder and light, components are created that make planes fly faster, farther, and more efficiently. First, engineers create a digital 3D model of the part with maximum precision. Every curve and cavity matters. Why? Because these components often operate in environments where even a millimeter can make all the difference, from engine efficiency to reliability. This digital model becomes a map for the 3D printer, which knows exactly where and how to build the required shape. Instead of a solid chunk of metal, ultra-fine powder, made from titanium, nickel, or Inconel, a super strong aluminum alloy, is used. It looks like sand, but the particles are so tiny they're almost invisible to the naked eye. The powder is loaded into a special reservoir, becoming the building material. The printer's working principle is simple yet genius. It melts the powder using a laser or an electron beam. The laser heats the powder to a temperature where it literally fuses into a solid metal structure. Then, another layer of powder is added, and the process repeats. This method is called selective laser sintering or melting. And here's the cool part. 3D printing can create even the most complex geometric shapes. For example, components with internal cooling channels that simply can't be made using traditional casting or milling. In conventional manufacturing, you often start with a big piece of metal and carve away the excess. It's not only time-consuming, but also expensive because so much material gets wasted. 3D printing flips the script. You only create what's needed, with zero waste. But the part isn't ready yet. After printing, it undergoes heat treatment, heating and gradually cooling to relieve internal stresses in the metal. Then comes final grinding, polishing, or machining to fine-tune precision. And of course, every part undergoes rigorous testing. Because here's the thing, if a part fails under pressure, the consequences could be catastrophic. Engine assembly takes place in a massive hangar, where every inch of space is filled with tools, engine parts, and technicians in overalls, all focused on creating something extraordinary. This is the final stage of building an aircraft engine. Here, individual components, like blades, compressors, combustion chambers, and casings, come together to form a single unit capable of lifting an airplane into the sky. It all starts with the engine casing, a giant metal cylinder that serves as the skeleton where everything else is attached. The casing is made from titanium or nickel alloys because it has to withstand insane forces. Engineers work like watchmakers. The casing is mounted on a massive rig to ensure perfect alignment. Then come the compressors, rows of blades responsible for compressing air before it enters the combustion chamber. Each blade is installed one by one, almost like decorating a giant wheel. Every single blade is manually inspected because even the tiniest defect could ruin the entire assembly. After the compressors, it's time for the turbines. These are the blades that convert gas energy into movement. They're installed with such precision that the gap between the blades and the casing is sometimes measured in micrometers. Next comes the combustion chamber, the engine's hell zone. This is where compressed air mixes with fuel and ignites. Engineers install special nozzles to ensure fuel is delivered evenly, and everything here has to be flawless. A nozzle at the wrong angle could reduce efficiency or even cause engine failure. Running through the entire engine is a central shaft, essentially the backbone. At one end of the shaft is a fan, a massive wheel at the front of the engine, and at the other end is the turbine. When the turbine spins from the force of hot gases, the shaft transfers this energy to the fan, which draws in air. Installing the shaft requires specialized robots. This part of the process demands surgical precision, as even the slightest misalignment can cause vibrations that could kill the engine. Once the engine's internal components are assembled, external systems are added. Fuel lines deliver jet fuel to the combustion chamber. The oil system ensures all moving parts are lubricated. And the electronics? The engine is packed with sensors that monitor temperature, pressure, RPMs, and much more. These systems are attached using cables, tubes, and bolts that must withstand both vibration and extreme temperatures. After assembly, the engine isn't immediately installed on a plane. First, it's mounted on a test stand that simulates real flight conditions, from takeoff to turbulence at altitudes close to 33,000 feet. This is the most spectacular stage. Running the engine at full power fills the air with a deafening roar, audible from miles away, and streams of blazing exhaust gases. The engine is pushed to its limits for hours as engineers test its strength, durability, and efficiency. Once the engine passes all tests, it's disassembled. Key components are rechecked, and then it's reassembled for final delivery. The finished engine is packed and shipped to Boeing or Airbus, where it becomes part of a new aircraft. Piece by piece, engineers craft the heart of an airplane, a marvel capable of carrying thousands of passengers across continents. Isn't this a modern masterpiece? Let us know if you'd like to see more videos like this. Think batteries are just boxes that store power? What if I told you it takes nearly 375 tons of rock and over 528,000 gallons of water to produce a single electric vehicle battery? Or that 70% of the world's cobalt is mined under terrible conditions, sometimes by children? In this video, you'll learn not just how lead-acid and lithium-ion batteries are made, but also the environmental impact they leave behind. Ready for some shocking facts that will change the way you see batteries? Let's get started. Car batteries are the heart of modern vehicles. They power the engine start, fuel electrical systems, and in the case of hybrids or electric vehicles, are the primary energy source for motion. But let's dive into their origins. The story of batteries begins back in the 18th century. In 1800, Italian scientist Alessandro Volta invented the first chemical battery, known as the voltaic pile, a far cry from the rechargeable batteries we know today. The first rechargeable batteries were created by French physicist Gaston Planté in 1859. These were lead-acid batteries, and remarkably, they're still widely used in vehicles with internal combustion engines today. The modern production of car batteries is a complex, multi-step process that requires precision and strict quality control. Let's break down the details using the most popular types. Lead-acid and lithium-ion batteries. For lead-acid batteries, the primary materials include lead, lead dioxide, sulfuric acid as the electrolyte, and polypropylene for the casing. Lead is either mined from ore or recovered from used batteries. It's then purified and melted for further use. Recovering lead from old batteries is a process that combines engineering expertise with a touch of modern-day alchemy. First, old batteries are dismantled, crushed in specialized machines, and sorted into lead, plastic, and electrolyte components. Think of it as a high-tech blender that breaks everything down into its core ingredients. The lead components are sent to smelting furnaces, where they're heated to temperatures exceeding 1,100 degrees Fahrenheit. At this stage, the metal transforms into a shiny silver stream that's mesmerizing to watch. Impurities and slag are separated, leaving behind pure lead, ready for new uses. The purified molten lead is poured into molds, where it cools and solidifies into perfectly uniform ingots. These ingots form the foundation for new batteries. The most fascinating part? This lead can be recycled endlessly. It has already lived in previous generations of batteries and might just end up powering your car. Lithium-ion batteries are made from key components like lithium, nickel, cobalt, manganese, graphite, and an electrolyte. Lithium is sourced either from salt flats in South American countries like Chile and Argentina, or from ore deposits in Australia. For lead-acid batteries, the electrodes are crafted from lead plates coated with active materials, specifically lead powder and lead dioxide. Picture this. Molten lead is poured into molds or rolled into thin sheets, which are then cut into precise shapes. These plates often feature multiple holes or grids to enhance bonding with the active material. The active material, which coats the grids, is prepared as a thick paste made from lead powder, water, sulfuric acid, and additives that enhance the chemical reactions. Let's take a closer look. The powder is produced by oxidizing lead in specialized mills, which grind it into a fine dust with the required properties. Watch as the grids move seamlessly along an automated conveyor, where the paste is applied to both sides. Rollers in the machine press the paste into the grids with just the right amount of force, ensuring even coverage and deep penetration into the cells. Excess paste is scraped off with blades, leaving a perfectly smooth layer. These paste-coated grids are then sent into special drying chambers. Inside, the paste loses moisture and hardens, transforming into the active material. We've covered lead-acid batteries. Now let me show you how lithium-ion batteries are made. In lithium-ion batteries, the anodes are made from graphite, while the cathodes are crafted from metal oxides, like lithium cobalt oxide. Next comes the assembly of the battery cells. These are the basic building blocks of the battery. In lead-acid batteries, cells are made by stacking several plates separated by separators. In lithium-ion batteries, the cells can be cylindrical, prismatic, or in pouch cell form. Electrolyte filling is the next step. In lead-acid batteries, a sulfuric acid solution is poured in. For lithium-ion batteries, an electrolyte made from organic solvents ensures the transfer of ions between the electrodes. The finished batteries undergo an initial charge to activate the chemical reactions. Each battery is tested to ensure it meets key parameters such as voltage, capacity, and resistance to discharge. Lead-acid batteries are then encased in polypropylene shells. Lithium-ion batteries, on the other hand, are often assembled into modules, which are later integrated into large battery packs for electric vehicles. Battery production is an energy-intensive process with significant environmental impacts. While lead can be smelted and reused, plastic casings are recycled into new shells, and the electrolyte is neutralized or processed. The situation with lithium-ion batteries, however, is far more challenging. Only about 5% of lithium-ion batteries are recycled. This is due to the complexity of extracting lithium, nickel, and cobalt. But the damage doesn't stop with neutralizing the components. To produce a lithium-ion battery for an electric vehicle weighing about 1,100 pounds, it takes 550,000 pounds of rock and nearly 530,000 gallons of water. This depletes Earth's precious resources. Producing just one EV battery generates anywhere from 3 to 16 tons of carbon dioxide. Imagine that. This is the same amount a gas-powered car emits over 5 years of driving. And that's just from one battery. The most troubling issue, however, is cobalt mining. About 70% of the world's cobalt comes from the Democratic Republic of Congo, where workers, including children, labor under horrific conditions. According to Amnesty International, more than 40,000 children are involved in cobalt mining. To make matters worse, mining often destroys local ecosystems, leaving lasting environmental damage. Recycling lead-acid batteries in countries with low environmental oversight, such as India and China, presents its own set of dangers. Lead dust and acid emissions often escape into the air, creating toxic clouds that harm the health of hundreds of thousands of people. Every single day, millions of batteries end up in landfills, posing a serious threat to the environment. But what if I told you those old batteries hold rare metals that can power the technologies of tomorrow? Lithium for electric vehicles, nickel for wind turbines, cobalt for medical devices, all hidden within the process of recycling. Want to know how toxic waste transforms into resources for the future? Stick around, an incredible process awaits. Battery collection starts with people. Individuals drop off batteries from phones and laptops. Auto repair shops contribute electric vehicle batteries, and businesses with lots of equipment also pitch in. Collection points can be found in electronics stores, supermarkets, or specialized recycling centers. This process is mostly hands-on. People bring in batteries, and staff or volunteers accept and log them. Large volumes of batteries from factories or auto repair shops are delivered by trucks to major collection centers. Specialized battery containers come equipped with sensors to detect their fill level. When a container is nearly full, it sends a signal to the recycling company. Some companies even use drones to check the status of large containers in remote locations. Batteries are sorted by type using both people and machines, as different batteries, like lithium-ion, nickel metal hydride, or lead-acid, can't be recycled together. At smaller collection points, like those in cities, workers manually sort batteries by examining labels, markings, and physical characteristics such as shape or color. Small batteries from smartphones or laptops are sorted one way, while larger electric vehicle batteries take a different path. At larger facilities, automated sorting lines take over. Machines scan batteries based on their size, weight, and the metals they contain. Advanced tools like X-ray analysis or spectroscopy determine the type of battery in front of them. Once scanned, batteries move along conveyors into designated bins, where they wait for the next stage. Even at automated factories, people are still part of the process. Operators ensure machines are sorting batteries correctly. If a problem arises, like a damaged battery case or missing label, workers step in to sort them manually. Batteries from electric vehicles or solar power systems are often too large for automated lines. This is where robots come in, helping dismantle these massive units into smaller sections, which are then sorted by material. No matter how much machines can do, people are still the heart of the sorting process. Most of the work is handled by employees at collection points and operators of sorting lines. Experts manually inspect damaged batteries, because machines haven't yet mastered the ability to detect every defect. Sure, machines are faster, but we can't do without human oversight just yet. In the end, every properly sorted battery is another chance to recover rare earth metals and reduce environmental harm. Next up, the batteries get shredded, like entering a pair of massive steel jaws. They're loaded into a machine that looks like a giant shredder, armed with industrial-grade steel blades. These blades are so powerful they can tear apart an electric vehicle's battery casing. The scene is pure metallic chaos. The sound of ripping, grinding, and snapping as the batteries are literally torn to pieces. Since batteries may still hold a charge, they're first frozen in liquid nitrogen. This cools the metals and minimizes the risk of fire. Some shredders operate in sealed chambers filled with inert gases to prevent contact with oxygen. There's even a more dramatic approach. In some facilities, batteries are burned with controlled electrical currents, leaving only the metals behind. The batteries are shredded into pieces ranging from several inches to fine powder, depending on the type of shredder. The blades spin at over 2,000 revolutions per minute, sending metal fragments clanging and crashing inside a protective chamber. The shredded material then moves through magnetic separators, which precisely extract ferromagnetic metals like nickel or cobalt. The remaining fragments continue along the conveyor belt. A fine black powder, known as black mass, settles into specialized containers. This is where the real treasure lies: lithium, cobalt, and manganese. Machines use dust collectors to literally suck up the powder, ensuring even the tiniest particles are recovered. The remaining materials that can't be recycled, plastics and traces of electrolytes, are flushed out using specialized liquid streams. At this stage, hydraulic crushers grind the leftovers into a slurry that's easy to filter. Engineers monitor the crushers and the temperature inside the chambers. Specialists analyze the crushed material to ensure all metals have been separated and no unwanted contaminants remain. If a battery is still charged or has defects, it can literally explode during crushing. But don't worry, the system has it under control. Any explosion is immediately suppressed with gases, and the process keeps running smoothly. Once the batteries are shredded and that precious black powder is collected, the real magic, science in action, begins. Metals that seemed locked away forever are recovered using two main methods: hydrometallurgy and pyrometallurgy. It might sound a bit technical, but the processes themselves are fascinating. So, how does it work? The battery fragments are submerged in special acidic solutions. Imagine massive vats filled with bubbling yellow-green liquid, typically sulfuric or hydrochloric acid. When the fragments are immersed, a chemical reaction occurs. Lithium, cobalt, nickel, and other metals literally dissolve into this metallic soup. To extract specific metals, a clever trick called ion extraction is used. Special reagents, such as organic compounds, are added to the solution. These reagents act like magnets, binding to particular metals. The result? Each metal settles into a separate layer. Once the metals are isolated, they're precipitated as salts or hydroxides. These appear as tiny white or colored crystals. For example, lithium settles as lithium carbonate, resembling fine sugar. Cobalt forms a vibrant blue precipitate, while nickel becomes a pale green powder. If hydrometallurgy is the gentle approach, pyrometallurgy is more like shock therapy for metals. Everything here burns and melts. The black mass is loaded into a massive electric arc furnace where temperatures soar to nearly 3,000 degrees Fahrenheit. The metals liquefy into molten layers, while plastic and other remnants simply burn away. The metals separate naturally, like oil and water, but at lava-like temperatures. Inside the furnace, several layers form. Heavy metals like cobalt and nickel sink to the bottom, while lithium remains in the slag, the lighter, upper layer. This slag is then broken apart and processed separately to extract lithium. Once cooled, the metals take the form of small ingots, shiny, smooth, and ready for reuse. Cooling after the pyrometallurgical process is typically a controlled procedure. If molten metals are left to cool on their own, it could take hours or even days. Plus, uneven cooling can lead to structural irregularities, which compromise the quality of the final product. That's why specialized chambers are used to regulate the cooling speed. For air cooling, ingots are placed on a conveyor under powerful fans. Imagine a giant hairdryer quickly cooling the metal surface. For water cooling, the ingots are submerged in tanks filled with water or special liquids for a faster process. As the red-hot ingots hit the water, they release dramatic clouds of steam, a visually stunning sight. There's also hybrid cooling, where the process starts with air cooling and finishes with water immersion. This method reduces internal stress in the metal. Controlled cooling ensures a uniform metal structure, which is critical for reuse in batteries. It minimizes cracks or defects that can occur due to rapid temperature shifts. The extracted lithium is used to create new batteries, ones that will power electric cars or even your phone. Nickel becomes part of wind turbines generating clean energy, while cobalt plays a vital role in medical devices. This process literally closes the loop. Old batteries give life to new technologies. Discarded batteries can become an ecological disaster. First, they contain toxic substances that contaminate soil and water. Second, mining for new rare earth metals not only depletes natural resources, but also damages the environment. Recycling solves both problems. Here's the kicker. The more batteries we recycle, the less we rely on mining new materials. It's a direct path to sustainable development. Despite lithium's growing popularity, only 1% of this metal is currently recycled. The main reasons: high costs and the complexity of the process. But researchers are developing new technologies that could revolutionize this in the coming years. Interestingly, even now, electric vehicle manufacturers like Tesla, Volkswagen, and BMW are investing in their own recycling plants to keep control over these valuable materials.